Today's lesson is on section 7.5, solving special types of linear systems. So far in this chapter 7, we've solved linear systems with three different methods. We've solved them by graphing, we've solved them by using substitution, and we've solved them using elimination. Those are the three methods we know how to solve a linear system. This next section just talks about some of those special cases that we can run into when we're solving a system. Questions in this section might just ask, like it says right here in the directions, either without solving, or even if we do solve, it doesn't matter, but determine if this system has one solution, no solutions, or infinitely many solutions. Again, those are the three things that could happen when we're solving a linear system. We might get one solution, just kind of showing these examples here on this grid. This is what it would look like graphically. If I have one solution, my two lines are going to cross. If I get the case where there's no solutions, remember, what does that mean in a linear system? Well, that means there is no one point that works for both equations or for both lines. So what happens in this case is if I graph those two lines, I get two lines that are parallel, lines that never cross. So this is the case where there's no solution because I don't have one common point between the two lines. They never intersect. And then the infinitely many solutions case is where maybe I would graph a line, and then I'm going to graph my second line. It actually falls right on top of the first one. It ends up being the exact same line, because that means that for both those lines, then all the solutions work, since the solutions are common to both equations. So any point that lies along that line will be a solution, since both lines fall on the same set of solutions. So those are the three cases that can happen, and that's what it looks like when we graph them. Now, these problems are saying without solving. And here's the thing, is we can actually tell before we even go to the graphing part. Again, we worked on graphing as a method. Before we even put pencil to paper to make a graph, there are ways to just look at our system, the two equations, and tell if it's going to be a one solution case, no solution case, or infinitely many. Like this first problem right here, and this is what I'll talk about in class as well. But this first problem, I have two different equations there. Y equals negative 2x plus 6, and y equals x plus 4. So we could graph both these equations, but I'll ask students right away before I even graph them if they have a guess, if they have an idea. Do they know, will this system, like the question asks, will it have one solution, no solutions, or infinitely many solutions? And usually after a little bit of thinking, students can start to pinpoint what's going to tell them, what will tell them if it's going to be one of those cases. What you can look at is the slopes of the lines. If we have parallel lines, we know that we have the same exact slope. So if I look at the slopes of these lines and I have two lines that have a different slope, well, then I know those lines must cross at some point. This one has a negative slope, y equals negative 2x plus 6, and the bottom one has a positive slope. So yeah, those lines are going to have to cross. I'll graph them just briefly here to show that. Y-intercept is 6, and this one goes down 2 over 1, down 2 over 1. It would look something like the line I have there. This second one, 4x plus 2, here's my y-intercept at 2. I'm going to go up 4 over 1, up 4 over 1. It would look something like that. So yeah, those lines are going to cross. But before I even make a graph, and in fact I don't even have to make a graph, students would be able to tell me just by looking at these equations in slope-intercept form if they're going to have one solution, no solutions, and infinitely many. It's by looking at the slopes. If the slopes are different, those lines are going to have to cross. Looking at this next example, this one also, if the direction said, tell whether this system has one solution, no solution, or infinitely many, we could again look at these equations since they're in slope-intercept form. Just from here, we can tell if they're going to have one of those three cases, or which one it will be. Well, this one has a slope of 4x, and this one has a slope of 4x. So, or I guess just 4. So both lines, if I'm graphing them, would go up 4 over 1, up 4 over 1. Before I even start graphing, I'll ask students, what do they think? What case will this be? And a lot of them can usually figure out that this will be the case where we have parallel lines. So that means it'll be no solution. If I graph these two equations, again, just to show this, y equals, my y-intercept is positive 6. I'm going to go up 4 over 1. Again, this line might look something like this, a pretty steep line. The second equation has a y-intercept of negative 2, but just like the first one, I'm going to go up 4 over 1. There would be my two lines, and again, if I draw them pretty nice, I'm going to see that those are parallel lines because they have the exact same slope. They're never going to get any closer to each other. They will never cross. since to get to the next point on the line, I'm always going up 4 over 1, up 4 over 1 for each one of them. So there's no way those two lines can intersect. So this is the no solutions case. But a student could find that, but without even graphing, without trying to use one of our methods, by just looking at the two equations as long as they're in slope-intercept form. One more example I have up here, before I get to the part where I'd like you to write something about this down, if you're taking notes along with me. This next one says y equals 4x plus 6 for the first equation in the system. Second equation says 2y equals 8x minus 12. In this one, I might have to actually get the equations in slope-intercept form first, though, to be able to compare them. So if I look at that first one is in slope-intercept form, this second one, if I'm going to determine before graphing if they're going to have a solution or not, I'm going to have to divide everything by 2 first of all. And I'll get y equals 4x minus 6. Now this one, so if I'm comparing this equation to my first equation, again, I would look at the slopes and say, yeah, the slopes are the same, so these equations are going to be parallel lines again, and then that means they're going to have no solution for this case. But I'm going to change this last equation for 1 second just to see what the third case is. If this happened to be a plus sign, if instead this was 4x plus 6, and I solved it and divided both everything by 2 and got to that equation, well, now all of a sudden I have the exact same equation. And remember, we talked about that case as well. What happens when I have the exact same equation for both equations in my system? Again, I'll asking the students. Usually we can figure out that, well, if I try to graph both those equations, then my green line would look like this, and my blue line would have the exact same y-intercept and slope, so it would look like that as well. And this is the case where there's infinitely many solutions. Again, not that every point works, just kind of explaining infinitely many solutions. Not that every single point on this grid works, but any point along these lines is a solution. Any single one of those red points and any one in between, any of those points is a solution. And there's going to be an infinite amount of them since the lines go on forever in both directions. So that's why we say infinitely many solutions. So those are my 3 cases. Those are the things that can happen. What we're talking about here in this section is before even graphing, you could figure that out by putting the equations in slope-intercept form. If you're a person who likes things pretty well laid out, exactly, what are we looking for then when we're doing these problems, looking for special cases, or just looking for what type of solution we'll have at all, here's what I'd like you to copy down. This in red. And also this box right here, which is in your book also in this same section, 7.5. But you can copy it down right here as well. I would like you to copy those 2 things down. It says when we're looking to try to identify, if we're just looking at a system, and we're going to solve it, but first we're just trying to figure out what kind of case is it. Does it have one solution, no solutions, infinitely many? If I go through the process of trying to solve it, using one of my methods, graphing, substitution, elimination, I'll run into one of my special cases as well. I'll be able to figure it out from there. But here's another way too. If I just put the equations in slope-intercept form, as I've got there in red, once you get the equations in slope-intercept form, if I look at the slope and y-intercept, I'll be able to determine how many solutions that system will have as well. The case where there's one solution, all I have to look at to see is are the slopes different? If the slopes are different, once I've got my equations in slope-intercept form, if the 2 slopes are different, then they're going to have one solution. That's the way it's always going to be. Excuse me. The no solutions case is when I have the same slope, but the y-intercepts are different. So if I look at like my case 2 I had up here, just kind of scrolling back to that for 1 second. This case right here, we had the same exact slope, but my 2 y-intercepts were different. That's the case where I'm going to have parallel lines because they both start at a different spot and along the y-axis. They both intercept the y-axis at a different place. But because they have the same slope, they'll never get any closer to each other because they're always increasing at the same rate or decreasing at the same rate. And then my last case, infinitely many solutions. Well, in that case, I'm also going to have the same slope, but I'm also going to have the same y-intercept as well. So that's the case where I pretty much have the same equation. I'm looking at it twice, almost like seeing double. Y equals 4x plus 2 and y equals 4x plus 2. That's the case where it's the same exact line, so I'd have infinitely many solutions for those cases. So in some of the problems today, all we need to do is get our equations in slope-intercept form and then just determine what type of system do we have. Are we going to have a solution, or a system with one solution, no solutions, or infinitely many? So looking at this first system here, if I want to get this first equation in slope-intercept form, right now it's close. It does have y by itself on one side, that term, but I need to have it as just one y, not half y. So if I multiply everything by 2, what is that going to give me? Well, that's going to give me y now, what I want, equals 4x plus 6. So that's my first equation. Looking at the second equation, this one I'm going to divide everything by 2 and see what I get. So I get y equals 4x plus 6, kind of like that example I talked about earlier. In this case, since I have the exact same equation for both of these, once I solve them and get them in slope-intercept form, this is the infinitely many solutions case. And so that's what I would put. If I did graph them, I would find it'd be the exact same line. So we say there's infinitely many solutions. Looking at this next example, this one I'll have to do a little bit more work to get them in slope-intercept form, but something still I'm definitely capable of doing. That first one, if I'm going to solve this equation for y, I'm going to have to subtract 4x for both sides first. That'll get rid of the 4x from the left side. Now I've got 2y equals negative 4x minus 6. And dividing everything by 2, I'm going to get y equals negative 2x minus 3. So that's what I've got for my first equation. Y equals negative 2x minus 3. The second equation, all I've got to do is subtract 2x from both sides. And this one will be in slope-intercept form for me. Y equals negative 2x plus 5. So if I look at my two equations, well, they have the same slope, so that tells me it's going to be one of these special cases. But the y-intercepts, they have the same slope, but the y-intercepts are different numbers. So this is the case where they're going to be parallel lines. So there's going to be no solution to this case. Those lines will never intersect. And so what we're saying, again, in these problems is that you wouldn't even have to go through all the steps of trying to find what the solution is or even graphing them. Sometimes just by looking at a system and getting the equations in slope-intercept form, that's enough. You can just from that point say, this is the type of solution, type of system it's going to be. A no solution or an infinitely many. Or if you determine that it's a case that has a solution, then we'll try to find that solution. Just going to go through these last two examples here also just to remind us too. Just say we're not doing graphing or we want to use one of the other methods to solve the system and we're worried about knowing when it's going to be a special case or not. Just remember that as you're solving, you'll run into the special case. Just we'll do the steps we normally do and the special case will present itself. We'll get to a point where we can find out that, nope, it's going to be a no solution or infinitely many. So looking at this first problem here, if I was going to solve this system, let's say I'm going to use elimination. I'm going to try to eliminate one of the variables. Well, maybe to do that, I would look at the second equation and say, well, if I times it by 2, the second equation, then I'll be able to eliminate either x or y in this case. So I'd get 2x plus 2y equals 6. Well, now bringing my first equation over, so I guess they're attached together in this case, so I'll just bring it over like this. 2x plus 2y equals 6. Now you can already maybe notice something funny going on about these two equations, but let's say we didn't notice anything quite yet. We're going to use elimination. So I would determine, well, I'm going to better subtract these two equations then to make that happen. And again, my suggestion is when you're subtracting, though, I'm just going to add instead, but I'm going to chop dash everything. I'm going to make everything the opposite sign of what it should be. So now I have negative 2x minus 2y equals negative 6. When I subtract all the like terms in this case, I'm going to get no x's and no y. So I'm just going to get 0 on the one side, and then 6 plus negative 6 giving me 0 as well. This is the case where you have infinitely many solutions, because if you look at your equation, what do you notice is that I have something that is true. 0 is equal to 0. So if I run into something like that, whether I'm doing substitution or elimination, if you ever run into this kind of case where you get 0 equals 0, or 5 equals 5, or negative 1,000 is equal to negative 1,000, whatever might happen, where all of a sudden you have the same number on both sides in one of those two methods for solving, then that's the case where it's infinitely many solutions, because you look at that final equation you got, and it is true, the variables all canceled out. Well, it is true that the left side equals the right side, so that's the case where it's infinitely many solutions. Going to this next example, let's say we were going to use substitution to solve this system. And again, just showing you that even if you use substitution, you'll run into one of the special cases and you'll know what happens. It's kind of similar for these two methods, substitution and for elimination. But let's say I'm going to subtract x from both sides in this equation and solve this equation for y. So I'll get y equals negative x plus 5. So then what I would do with this one, again, using substitution, remember y equals this expression right here. So I'm going to plug that in for y and see what happens in my first equation. So I'll get 2x plus 2 times, well now I have negative x plus 5 in there, and that's going to be equal to 6. And then I'll just start solving it like a multi-step equation. 2x plus, well now I have negative 2x plus 10 equals 6. And here's the part where my x's cancel out. 2x and negative 2x, those are going to cancel. So what am I left with in substitution, using that method in this case? Well, all my variables have canceled out, and I'm left with 10 is equal to 6. Well, again, if you see that, the first thing you do is just throw a slash through that, because that's not true. 10 is not equal to 6. This is the no solutions case. If you were doing elimination with this method, you would run into something very similar. You'd at some point run into the case where you'd have something on the left side and something different on the right side. So again, it could look like negative 1 equals 0. Or negative 22 equals 55. You know, whatever the numbers might be. Either way, if you get two different answers, or two different numbers on each side of the equation, that's the no solutions case. And I'll just show this last example just as one more reminder, though, I mean that not everything is a special case. What does it look like, again, when we just get a solution, when there's a one solution case, where the lines do cross, if I graphed them? Well, I could use elimination for this particular one, subtract both equations. Or again, I'm just going to add and chop dash everything. In this case, I would get y equals 1. So I mean, remember that can happen. Just remind us, I've shown this a lot of special cases in this lesson. But remember, you can just get y equals 1, and you can plug that back into one of the equations and get 2x equals 2, or 2x plus 2 equals 6. Subtract 2 from both sides. Get 2x equals 4, and then get x equals 2. I mean, that can happen also. You can just get an answer like 2, 1. So just don't forget about that. But yes, there is definitely cases where you just get a solution. But the special cases are ones we can be aware of. And sometimes, like I showed in the first set of examples, before you even go ahead and graph it, if you just look and get the equations in slope-intercept form, you can look at the slopes and y-intercepts. And that can be enough to tell you if it's going to be a special case or if you'll get a solution.